The flow above a wavy riverbed is given in Cartesian coordinates by the velocity field Vx equals big V plus ak e to the minus ky sine kx, Vy equals ak e to the minus ky cos kx, where big V is much bigger than a times k. What we have to do first is sketch the flow field, then show that it satisfies conservation of mass if the flow is incompressible, and then show that the vorticity is zero everywhere. So let's start by sketching the flow field. It's always a good idea to start by drawing in the coordinates. So that's the y-axis there. Let's draw the x-axis horizontally across the page. Now, the first thing to note is this comment that v is very much bigger than ak. It means that this v term at the beginning in the vx will be very much bigger than the other two terms. That means that globally the fluid motion is in that direction at a velocity v, and that the other terms are really just additions to that, small additions to that. Furthermore, we have here e to the minus ky terms in both of these small further additions, which means that as y increases, as y gets larger, these terms get smaller and smaller. So we can tell that at large values of y, essentially what we have is a velocity moving horizontally in the positive x direction. Now let's turn our attention to values around y equals to 0, where the e to the minus ky terms become roughly equal to 1. We'll see that the velocity in the y direction then becomes ak cos kx, and that means that it has a maximum at x equal to 0 in the upwards direction, the same maximum at x equal to 2 pi over k, again in the positive direction, and then a maximum in the other direction at x is equal to pi over k. Now these, of course, this upwards-downward motion is just superimposed onto that global horizontal motion, so what we have is the horizontal with a bit of upwards at that point there, the horizontal with a bit of downwards at x equal to pi over k, and horizontal with a bit of upwards at 2 pi over k. And now we can begin to fill in some of the other points. These will be going horizontally when exactly halfway between 0 and pi over k and 2 pi over k, and this will be repeating itself all the way along the x-axis. So now we can start to draw in a streamline at the bottom that joins up these velocity vectors, and there's our streamline at the bottom. Now let's again turn our attention to the e to the minus ky term. What that's saying is that as you go up the y-axis in this direction, the velocities are just getting exponentially smaller. So a little bit further up we'll have the same sort of streamline shape, but it'll be a little bit with a smaller amplitude, and then further up the amplitude will be even lower. So we end up then with the flow over a wavy riverbed. Now we have to show that this flow satisfies the conservation of mass. If you go back to the notes, you'll find the conservation of mass written in vector form is d rho dt is equal to minus the divergence of rho v, where v is a vector. Now, we're told that the flow is incompressible, which means that rho is a constant. And this means that this term simplifies to 0 equals minus rho comes out because it's a constant of the divergence of v, and because rho is a constant, this means simply that the divergence of v is equal to 0. Now the strict way of writing out this expression in Cartesian coordinates is this, and then we work that out noting that ex dotted with ex is equal to 1 and ex dotted with ey is equal to 0, etc. Now in Cartesian coordinates, but only in Cartesian coordinates, you can use a shorthand for this. You can say that this is equal to d by dx, d by dy, that's the nabla operator there, or the upside down triangle, dotted with Vx, Vy, written as a vector like that. And you can see straight away that that simplifies to dvx by dx plus dvy by dy is equal to 0 if it's to satisfy conservation of mass. Now, as an aside, I want to show why that works in Cartesian coordinates but not in polar coordinates, for example. And it's because in Cartesian coordinates, no matter where you move to in your coordinate system, the vectors Ex and Ey always stay pointing in the same direction. Now that differs from polar coordinates, for example. In polar coordinates, you look at a certain value of theta, you get the ER vector looking like that and the E theta vector orthogonal. But if now you move to a different point, the ER vector has changed direction, as has the E theta direction. So you find that the coordinate system, or the direction of the unit vectors, changes as you move around in the space. What you find is that d by d theta of ER, the unit vector in the r direction, is not equal to 0, and d by d theta of E theta is not equal to 0 either, whereas in the Cartesian case, d by dx and d by dy of any of the unit vectors Ex or Ey is equal to 0. So scrolling back up, what this essentially means is that this expression here does multiply out to become exactly the same as that expression there, in the case of Cartesians, using the Cartesian shorthand on the left here. But had we done it in polar coordinates using a similar sort of shorthand, we'd have made a mistake. So to summarize so far, conservation of mass in the case of an incompressible flow has given us this equation. We've reduced this in the Cartesian coordinates to the second equation, and we were given at the beginning these expressions for Vx and Vy, and now we have to substitute them in to the equation on the left to check that it is equal to 0. Now this is a relatively simple thing to do. Let's do dvx by dx. Dvx by dx is equal to, well, the v doesn't have any x term in it, it's going to be a k e to the minus ky. Sin kx is going to become k cos kx. So we've got a cos kx, and then that becomes k squared. dvy by dy is equal to a k doesn't change, e to the minus ky. Now we've got an extra minus k to put in there, and the cos kx doesn't change. Add those two together and you get, of course, 0. So we've confirmed that the divergence of v is equal to 0, and therefore that the law of conservation of mass in an incompressible flow is conserved. And the next thing we have to do is show that the vorticity is 0 everywhere. Now the vorticity is defined, well, it's often given the symbol omega. It's defined as del, or nabla, crossed with v, or the curl of v. Now we can again use our Cartesian shorthand here. So we've got d by dx, d by dy, crossed with vx, vy, and that's equal to dvy by dx minus dvx by dy. And we can substitute in our values, or expressions for vx and vy again, and we find that we get minus a k squared e to the minus ky sin kx, that's the dvy by dx, plus a k squared e to the minus ky sin kx, and that's equal to 0. So we have that the curl of v is equal to 0 In other words, the flow is what we call irrotational. Now this has very important consequences for Bernoulli's equation that you can find in the lecture notes. For interest, you might like to work out where the pressure will be highest and where it will be lowest, and then in fact derive an expression for the pressure, noting that big V is much larger than A times K, so some terms will be much bigger than others.